and he received PhD degree from the University of British Columbia under the supervision of Professor Herman M. Dorman. Now he is professor in the Department of Electrical and Computer Engineering of the University of British Columbia. He is a lifetime fellow of the IEEE and also a fellow of the Canadian Academy of Engineering. He is registered professional engineer in the province of British Columbia, Canada.
Thank you very much, Mr. Chairman. So here is a time domain guy who's going to talk about frequency domain solutions. Let's see. So this work was done mostly by my student, Arash, and then we have a couple of co-authors from BC Hydro because they've been using this method to validate some of their results. So the presentation is follows these aspects. So BC Hydro is doing transient overvoltage studies on their 138 kilovolt sub-transmission system that has a large variety of lines and ground resistivities, etc. So we're going to compare the proposed frequency domain solution with the numerical Laplace transform, as Dr. Naredo did, but we're going to be looking at it from a slightly different point of view. These TOV studies are important for the utility company, mostly because TOV can be hazard for crews. And okay, sorry about that. So it's they have the mandate to perform this TOV analysis carefully. In terms of simulation tools, BC Hydro, this group in particular uses the EMTPRB. So they use a frequency-dependent line models. Normally they use my model, version 2 of it, not version 1, as I was saying on Monday. And they find it quite sufficient, even though the type of lines they have is pretty double circuit, asymmetrical configurations, etc. For verification, they also use the ULN model. At UBC, we have access to PSCAT, EMTPRB, and then so we use both. So for these comparisons, I'm going to present, we're going to use the one that gave us the best results, whether it was PSCAT or EMTPRB. Now for the frequency domain solutions, we coded that in just using MATLAB, and we coded the proposed Discrete-Time Fourier series method and the numerical Laplace transform. It's important when we do frequency domain or Laplace domain mappings or transformations to understand that we actually have 4 possibilities. We have discrete time, discrete frequency. When we do that, we work on a finite time window and a finite frequency window. And that's where we develop the method I'm going to present. So it is discrete time Fourier series in signal processing that's known simply as the discrete Fourier transform. There is a 1 over n being the number of samples difference, but that's totally minor. And it's also the basis for the FFT algorithm, which is a fast way of doing a DFT. When you work in, or the numerical Laplace transform was conceived based on the Fourier transform. So the original thought was to take the Fourier transform of a time signal. As such, the time signal is considered continuous, so your delta t is very small, which gives you an infinite frequency window, and vice versa. You assume that the frequency transform is continuous, which when you come back to time, gives you an infinite time window. As I said, when you use the DTFS, the time window and the frequency window are finite. So this is a very brief review of the numerical Laplace transform, which was advanced throughout the years. If I get the history correct, Professor Naredo should correct me on this. was Moulinex in 1965. Then Professor Martin Wedepol used it extensively. He developed a frequency domain solution program. Professor Ametani incorporated the FFT within the frequency domain solution. And I got here Wilcox in 1978 and Professor Naredo's group from the year 2002 or so, or maybe earlier than that, I'm not sure. So the basis of the, again, it's a Fourier transformation, and the Fourier transformation idea is that you can express a time signal as the sum of exponentials, basically, exponentials of different frequencies. When it's a continuous time signal, you have all the frequency components in it, and of course, practical limitations tell you that you cannot use an infinite frequency window. Therefore, you have to chop that window to a reasonable width, which is normally the maximum frequency of interest. To compensate for some of the problems, in the numerical Laplace transform, you define two parameters. One is the damping factor, sigma, and the other one is a windowing function, so that you limit your frequencies to a certain maximum frequency. In the method that we propose now, which is as old or older than the other methods, but it's based on digital signal processing. In digital signal processing, you can, if you have a finite number of samples in time, say I have nine samples here, in a certain time window, you can match exactly each one of these time samples using 9 frequency components. So there is a one-to-one correspondence between the number of frequency components and the number of time samples. In that case, that's what it is. It's an exact mapping between time and frequency. So this gives you a discrete time signal, which is the same as we do when we do an EMTP simulation. In EMTP simulation, the time points are separated by a delta t. We do exactly the same here. So again, it's a finite number of time samples that can be represented by a finite number of frequencies exactly. So we don't have to deal with the issues of truncating frequency for one thing. And yeah. So the way this works is the following. And the main idea here is what I'm going to say. If you have an input function of whatever shape it is, let me say it backwards. Whenever you run a time domain simulation, you want the results from 0 to Tmax. That's any time domain study, you want to know the solution from 0 to Tmax. Well, we do the same here. We're going to have a certain input source function that we're going to apply between 0 and Tmax. And that's fine, and that can be any arbitrary source. It's not, we don't have to pre-know, answering the previous question by Dr. Golling, we don't have to know or limit our input sources to a known wave shape. It can be anything, and as long as we know what's going to be between 0 and Tmax. Now, the main point here is that the system is going to start responding to all the samples of the input function. So you will respond to the sample at t equals 0 according to the time constants of the system response. And in particular, it will respond to the last sample of the input function. So it will take some time delay for the effect of the last sample of the input function, which is at Tmax, or actually Tmax minus delta t, that's a detail. It will take a certain time for the system to respond to the last sample of the input function. So if we allow for the response to that last sample to be contained in our time window, then we have all the information of that transient. And that's the basis of this method. We will contain all the response of the system from 0 to Tmax in our time window. In that case, we can map exactly this number of samples in time to corresponding frequencies, solve the system in frequency and come back to time with that exact mapping that the discrete Fourier transform provides us with. Now, how do we know the time constants? That's the only thing that this method needs. You need an eigenvalue routine that will tell you the eigenvalues or poles of your system. Once you know that, the slowest time constant determines how much you have to add to Tmax in your time window to have the complete information. So, as Professor Narello mentioned, and I can re-emphasize, some of the problems of the numerical Laplace transform are the truncation in frequencies, the separation between frequencies, those produce aliasing and Gibbs effects, with what we call the CDTFS, we don't have that source of errors. Our only preoccupation, our only condition is that all the transient responses will be contained in our time window. I'll skip this one and I'll go directly to the simulation results. This is, as I said, the TOV study in BC Hydro's 138 subtransmission network, which is pretty extensive, and it has a large variety of sources, different types of transmission lines, etc. There are some of the types of transmission lines. We go from double circuit, single circuit, vertical lines, horizontal lines, all the possible line configurations here, and a variety of resistivities, a wide range of resistivities as well. In frequency domain, it's straightforward to model transmission lines. You just use the pi circuits with the long line correction, the frequency correction. These are the parameters for the simulation that we perform in energizing that subtransmission system. So we're going to simulate up to 0.1 seconds of simulation time, and all the other parameters are here. So this is the first result in which, and the important thing here is the time window. So here the simulation time is 0.1 seconds. For the proposed method, we need a time window of 0.3 seconds, which is 3 times the simulation time. Again, that extra time is to allow the exponential responses to decay. When you use the numerical Laplace transform, the standard procedure is to take the time window as Tmax. There are some researchers that recommend to take more than that, but basically it's Tmax. So here you can see the comparison between I find it difficult to point from this angle, but we're comparing the proposed method, the numerical Laplace transform, with different damping factors, because the damping factor has an effect. And for the best window in that, there are several windows, so we use the window that work the best. So you can see that at the beginning, the results are reasonable, but they begin to deviate very quickly for the numerical Laplace transform with respect to the discrete Fourier series. This is just the detail. It's numerically, the NLT should use what is called outsampling as opposed to regular sampling. If you use regular sampling, you have more numerical problems, according to my student. Okay. Anyway, so the important part here is, to us, is that time window that has to include all the transients. So in this example, for the same Tmax, we made the time window of the Laplace transform 3 times the Tmax, which is the same time window we use for the discrete Fourier transform. And you can see there is a bit of an improvement in the results. Now, why not continue that? Let's make the time window of the Laplace transform even wider. And here we got a good match between the Fourier series, or the Discrete-Time Fourier series, and the numerical Laplace transform. so at the expense of increasing the time window of the Laplace transform. What that tells us is that in the end, the Laplace transform also needs to let the transients of the system die down. The trick that the Laplace transform uses to not have to do that is the damping factor, but that's not enough, really. You have to let the natural transients of the system to die down. You cannot just force them with the sigma to be contained in the window. So this is now a comparison of this Fourier or Laplace domain solutions with the EMTP frequency-dependent transmission models. So we compare the results with FD-line from RV and ULM from PSCAT. To be fair, we use one of each. And you can see that they compare fairly well. So the time domain models match the most accurate frequency domain models very well. And again, this was the case with multiple line configurations, multiple ground resistivities, etc. Blowing up this a bit to try to detect the differences, you can see that that FD line tends to be a bit more accurate than ULM. ULM is the red. So the differences in the ULM tend to be a bit bigger. That can be a long discussion on its own as to the reasons for that. But this is our experience in a number of simulations, in particular for this case. As a conclusion, to conclude, we are proposing a new frequency domain solution tool based on the very simple Fourier series rather than the transform, so that we avoid having to chop frequencies. We avoid sampling or a continuous time function and a continuous frequency function. We just start off with samples in time and samples in frequency. So doing that, we find out that if we are able to contain all the time constants of the system within our time window, the results are very accurate. One important thing here, as a side comment, is that the frequency-dependent models in the EMTP are very accurate. And that's really amazing because the frequency domain models have to do lots of acrobatics to fit transfer functions for the characteristic impedance or admittance, to fit the propagation function, to fit the transformation matrix in the case of ULM. Despite having to do all of that, they still give results that compare very well to the frequency domain results. And I want to finish this with the last point here, the fact that the EMTP line models and the frequency domain line models give highly similar results, proves that they're both right. And I always remember Martin Wedderpom, when he was at UBC, one day he proposed to me, Jose, let's compare your frequency-dependent line model with my frequency domain solution. And so we did that. He used his program, I used my program, and the results were similar to what I just showed today. And he says, oh, Jose, I'm very happy. That proves that my program works. Which is true. That proves that both programs work because the mathematics are so different. And it's totally amazing that after making all these terms, they both give the same results. So thank you for your attention.